This is your need to know. This is your need to know.
All right, get ready, because today we're taking a deep dive into something pretty amazing. We're talking about blazars.
And yeah, these are some of the most powerful objects in the universe. Imagine like cosmic lighthouses shining across billions of light years.
Okay, cosmic lighthouses. I like that.
Yeah.
But I gotta ask, what makes them so bright? What's going on there?
Well, it all starts with a supermassive black hole, millions, even billions of times heavier than our sun. And it's surrounded by this swirling disk of gas and dust. We call it an accretion disk.
So like a giant whirlpool, and in the middle is this monster black hole just pulling everything in.
Exactly. And as all that stuff spirals in closer and closer to the black hole, it heats up and it starts glowing, emitting light across the entire electromagnetic spectrum. But here's where things get really interesting. Blazars also have these incredibly powerful jets shooting out from their poles.
Jets, like geysers of energy erupting from the black hole.
Exactly. Imagine beams of superheated plasma just blasting out into space, propelled at a significant fraction of the speed of light.
Hold on, a significant fraction of the speed of light. That's mind-blowingly fast.
It is. And the key thing about blazars is that one of these jets is pointed almost directly at us.
Oh, wow. So it's like we're staring right into the beam of a cosmic flashlight.
That's a great way to put it. And that's why they appear so incredibly bright to us, even though they're billions of light years away. It's that alignment that makes them stand out, even amongst the billions of galaxies in the observable universe.
So we've got these supermassive black holes, the accretion disks, these crazy powerful jets, and they're all working together to create these dazzling objects. But before we go any further, I'm kind of curious about the sources we're using for this deep dive. What kind of information are we working with here?
Well, we've got a really interesting mix. We've got encyclopedia entries, scientific articles, and even real observational data from telescopes like the Event Horizon Telescope.
Yeah.
You know, the one that captured the first ever image of a black hole.
Oh, right, yeah. So we're combining the big picture overview with the real nitty-gritty details.
Exactly. And by combining these sources, we're hoping to answer some pretty cool questions. Like, how do these jets actually form and reach those incredible speeds? What makes their brightness fluctuate? Can we actually see these jets change direction over time? And what can blazars tell us about the evolution of galaxies on a grand scale?
So many questions. This is going to be awesome. But let's start with the basics. Like, what's the anatomy of a blazar? We've touched on it, but I want to really understand what's going on inside that central engine.
Absolutely. So we've got the supermassive black hole at the center. That's our powerhouse. And then there's the accretion disk, that swirling mass of gas and dust. But there's another key component here. It's a hot, opaque region further out called a toroid.
Okay, a toroid. What's that?
Well, imagine it like a giant donut surrounding the black hole in the inner part of the accretion disk. This toroid, it absorbs energy from the central regions of the blazar, and then it remits it as infrared radiation.
Oh, so it's like a cosmic transformer, converting energy from one form to another.
That's a great way to think about it. And by studying the infrared emissions from the toroid, we can actually learn a lot about the environment around the black hole.
That's wild. It's like these different parts of a blazar are like giving us clues about the extreme physics happening at its core.
Exactly. And it gets even more interesting when we consider that there are actually two main types of blazars. BL-Lacertae objects and OVV quasars.
Wait, two different types? So are we talking about like completely different beasts here? Or is there some connection?
That's a great question. And it brings us to the concept of unification. The prevailing theory is that both BLS objects and OVV quasars are actually the same type of object, just viewed from different angles.
So it's all about perspective.
Exactly. Imagine you're looking at a flashlight. If you look directly into the beam, it appears incredibly bright, right? That's like observing a blazar head-on. But if you view the flashlight from the side, the light's much dimmer. That's analogous to observing a less luminous active galactic nucleus.
So it's like we're catching these cosmic lighthouses from different angles, and that's why they appear so different to us.
Precisely. And this unified model is supported by the fact that both types of blazars show similar characteristics, like rapid variability and emission across the entire electromagnetic spectrum. The key difference is just the orientation of their jets. relative to our line of sight.
Okay, so we've got these jets, and they can be pointed right at us or at a slight angle. But you mentioned earlier that these jets travel at, like, a significant fraction of the speed of light. What does that mean for our observations? Shouldn't something moving that fast just be a blur?
Well, that's where things get really, really mind-boggling. We're talking about speeds so extreme that they lead to something called superluminal motion.
Superluminal motion. That sounds like something straight out of science fiction.
It almost is.
Hmm.
At first glance, it appears as if these jets are actually exceeding the speed of light, which of course is impossible according to Einstein's theory of relativity.
Wait, so are we, like, breaking the laws of physics here?
Not quite. It's all an illusion, a trick of perspective caused by the jet's orientation and the finite speed of light.
Okay, you're going to have to break this down for me. How can something appear to be moving faster than light without actually breaking the laws of physics?
Okay, so imagine a spotlight sweeping across a distant wall. The spot itself can appear to move faster than the spotlight is rotating, even though the light from the spotlight is traveling at a constant speed.
So it's like our perception is being tricked by the geometry of the situation.
Exactly. And with Blazars, we have a similar scenario. The jet is pointed almost directly at us, and the material within it is moving at a significant fraction of the speed of light. And this combination makes it seem like the jet is moving faster than light, even though it isn't.
Okay, so it's all about angles and the time it takes for light to reach us. That's wild. We're seeing something that seems to defy the laws of physics, but it's all explained by Einstein's theories.
It really is a testament to the power of physics to explain even the most bizarre phenomena in the universe.
Absolutely. So we've established that blazars have these incredibly powerful jets that can appear to move faster than light. What else can we learn by studying them? Are there any, like, specific examples that stand out?
Oh, absolutely. One of the best studied blazars is called 3C279. And thanks to the Event Horizon Telescope, we now have these incredibly high-resolution images of this cosmic powerhouse.
Wait, the same Event Horizon Telescope that gave us the first image of a black hole?
The very same. In 2020, the EHT team pointed their telescopes at 3C279. And what they found was truly remarkable.
Okay, spill the tea. What did they see?
The images reveal these two bright, elongated regions. They're labeled C0 and C1. And they're thought to be part of the jet. And what's fascinating is that they were observed to change in brightness and structure over just a few days.
Wow. So these jets aren't just like static beams. They're dynamic and constantly evolving.
Exactly. And the observations also showed that the jet components were moving in a non-radial fashion, meaning they weren't simply moving outward in a straight line. They were exhibiting more complex three-dimensional motions.
Okay, this is getting juicy. What kind of explanations do scientists have for these strange motions and the overall elongated shape of that C0 region?
Well, one possibility is that we're seeing magnetic reconnection events happening within the jet. This is where magnetic field lines break and reconnect, releasing enormous amounts of energy.
So it's like a cosmic short circuit happening within the jet.
That's one way to think about it. Another possible explanation is that the elongated C0 region is a shock front, where material in the jet is colliding with slower-moving material. This collision would also release a tremendous amount of energy, potentially explaining the bright emissions we observe.
Okay, so we've got magnetic reconnection, or a shock front, as potential explanations for what's going on in that C0 region. What about the non-radial motions of the jet components? What could explain that?
Well, that's where the idea of a precessing jet comes into play.
Precessing jet. You're going to have to define that one for me.
Sure. Imagine a spinning top. As it slows down, its axis starts to wobble, tracing out a circle. This wobbling motion is called precession. And it's possible that something similar is happening with the jet in 3C279.
So the jet isn't perfectly straight. It's kind of like wiggling around as it blasts out into space.
That's the idea. And this precession could explain those non-radial motions observed by the EHT. It also lends further support to the unified model of active galactic nuclei, where the different types of AGN we observe are simply due to different viewing angles.
So we're piecing together this picture of blazars as like incredibly dynamic systems with jets that are not only blazingly fast, but also potentially bending and precessing as they interact with their surroundings. What else can we learn by studying these cosmic powerhouses? Are there other ways to observe them besides like traditional telescopes?
There is. Scientists are now using this exciting new approach called multi-messenger astronomy.
Multi-messenger astronomy. That sounds intriguing. What's that all about?
It's this revolutionary way of studying the universe by combining information not just from light, but also from other messengers. like neutrinos and cosmic rays.
Neutrinos and cosmic rays, those are some pretty exotic messengers. What kind of information do they carry?
Well, they carry valuable information about some of the most extreme environments in the universe, including blazars. Neutrinos are these tiny, almost massless particles that rarely interact with matter, so they can travel vast distances across the cosmos undisturbed. And cosmic rays are high-energy particles that are constantly bombarding Earth from all directions.
So it's like having multiple spies reporting back from the front lines of the cosmos, each providing a different piece of the puzzle.
That's a great analogy. And one of the most exciting discoveries in multi-messenger astronomy came in 2017, when the Ice Cube Neutrino Observatory in Antarctica detected a high-energy neutrino that was traced back to a blazar called TXS 0506 plus 056.
Wow. So we're not just seeing light from blazars, we're also detecting these ghostly neutrinos streaming out of them. What does that tell us?
It's a major confirmation that blazars are also powerful accelerators of cosmic rays. We've long suspected that blazars were responsible for at least some of the cosmic rays we detect, but this neutrino detection provided, like, the smoking gun.
So these blazars are like cosmic particle accelerators shooting out both light and particles at incredible speeds.
Exactly. And by studying these particles alongside the light, we get a much more complete picture of what's going on in these extreme environments. It's like having a front row seat to the most powerful particle accelerators in the universe.
This is blowing my mind. So we've got these blazars beaming light, neutrinos, and cosmic rays at us. What other secrets do they hold? I mean, what else can we learn from them?
Well, one of the big questions that scientists are trying to answer is how blazars impact the evolution of galaxies. We know that supermassive black holes reside at the centers of most galaxies, but how does the activity of a blazar affect the galaxy it lives in?
That's a big question. What do our sources tell us about the connection between blazars and galaxy evolution?
Well, there's some fascinating research that's been done using the Hubble Space Telescope. Observations have shown that BL-lac objects, which are one type of blazar, reside almost exclusively in elliptical galaxies.
Elliptical galaxies, those are the ones that are like kind of smooth and oval shaped, right?
Exactly. And these elliptical galaxies that host BL-lac objects, they tend to be large and luminous, with a relationship between their size and surface brightness that's typical of elliptical galaxies in general.
So BL-lac objects and their elliptical host galaxies seem to fit a certain pattern, but what does that pattern tell us about the connection between blazars and galaxy evolution? Is there a cause and effect relationship?
That's what scientists are trying to figure out. And one observation that's throwing a wrench into things is the lack of a strong correlation between the brightness of the host galaxy and the brightness of the BL-lac object itself.
Wait a minute, so you're saying that a brighter galaxy doesn't necessarily mean a brighter blazar?
Exactly. And that's a bit of a head-scratcher, because some theories suggest that the growth of a supermassive black hole and the evolution of its host galaxy are closely linked.
Yeah. Okay, so if the black hole is gobbling up more material and the blazar is getting brighter, shouldn't we see the host galaxy getting brighter too?
That's the expectation, but the observations haven't quite borne that out yet. It could mean that the relationship between black hole growth and galaxy evolution is more complex than we initially thought.
So the mystery deepens. Is there anything else that can shed light on the connection between blazars and galaxy evolution?
Well, another intriguing piece of the puzzle comes from studying the evolution of blazars over cosmic time. Research has shown that high-luminosity blazars evolved faster than their low-luminosity counterparts, meaning they were more common in the early universe.
So in the grand cosmic timeline, blazars were more active and prevalent in the past.
That's what the data suggests, yeah. And this finding opens up even more questions about how these objects form and evolve over billions of years.
It's like we're trying to piece together a cosmic jigsaw puzzle, and we've got some of the pieces, but we're still missing the big picture.
Exactly. But every new discovery, every observation, brings us closer to understanding the role these fascinating objects play in shaping the universe we see today.
Speaking of fascinating observations, there's this one particular galaxy that's caught the attention of scientists. It's called PBC J23333.92343, and it seems to have undergone a dramatic transformation.
Ah, yes, PBC J2333332333, a case study in the dynamic nature of galaxies. This galaxy appears to have shifted from being a giant radio galaxy to a blazar.
Hold on a second. You're telling me that this galaxy changed its identity. How is that even possible?
The key to this transformation lies in a change in the direction of the jet. Remember we talked about how the orientation of the jet determines whether we see a blazar or a less luminous type of AGN? Well, in the case of PBC J2333333, 23343, it seems that the jet has shifted its orientation so that it's now pointing almost directly at us.
So it's like this galaxy was hiding its blazar nature all along and then suddenly decided to unveil itself to us.
In a sense, yes. And what's even more intriguing is that this dramatic shift in jet direction might have been caused by a major event, like a galaxy merger.
Okay, so we've got two galaxies colliding, their central black holes merging, and this chaotic dance somehow causes the jet to, like, reorient itself.
That's the working hypothesis. And it highlights the fact that blazars are not like isolated phenomena. They're embedded within galaxies, and their activity can be influenced by the events and interactions that shape those galaxies.
So PBC J2333.92343 is a prime example of how, like, dynamic and ever-changing the universe can be. Even on the grand scale of galaxies, things are constantly in motion, evolving, and transforming.
Absolutely. And it underscores the importance of studying these objects, not just for their own sake, but also for what they can tell us about the larger processes at play in the universe.
This has been an incredible journey so far. We've learned about the structure of blazars, their mind-bogglingly fast jets, the phenomenon of superluminal motion, the insights from the Event Horizon Telescope, the world of multi-messenger astronomy, and the connection between blazars and galaxy evolution.
And we've only just scratched the surface. There's so much more to explore about these enigmatic objects.
Well, don't worry, folks. We're not done yet. In part 2 of our deep dive into blazars, we'll delve into the mysteries of their brightness temperatures, the mechanisms behind their energy production, and the challenges of modeling these complex systems.
Stay tuned, because we're about to venture even deeper into the heart of these cosmic powerhouses.
This is your need to know.
Welcome back to our Blazar adventure. We've been on quite a ride so far, exploring the anatomy of these cosmic powerhouses and uncovering some truly mind-bending phenomena, like those super fast jets that seem to, like, defy the laws of physics.
It's certainly been a fascinating journey, and now we're ready to delve even deeper into the mysteries of blazars.
Exactly. We've talked about how incredibly bright they are, but I'm kind of curious, how do scientists actually measure their brightness? Especially when those jets are pointed right at us. It seems like it would be tricky to get an accurate reading, right?
You're right. It's not as simple as just, pointing a telescope and measuring the amount of light we see. That's where the concept of brightness temperature comes in.
Brightness temperature. Okay, so what exactly is that?
It's a way to measure the intensity of radiation at a specific frequency. So it's not just about how bright something looks to our eyes. It's about how much radiation it's pumping out at a particular wavelength.
So it's like a measure of how hot the radiation is, in a way.
That's a good way to think about it. And when it comes to blazars, we're often dealing with extremely high brightness temperatures, which tells us that those jets are incredibly energetic.
But here's where I'm getting a little confused. One of our sources, the research article on 3C279, it mentions that the Event Horizon Telescope observations actually revealed surprisingly low brightness temperatures for this blazar. That seems counterintuitive, given everything we've discussed about how powerful these jets are.
That's a great observation, and it points to one of the biggest mysteries surrounding blazars. The low brightness temperatures, measured by the EHT, they challenge our understanding of how energy is dissipated within the jet.
Energy dissipation. So we're talking about how the energy carried by those super fast particles in the jet is converted into the radiation we observe, right?
Exactly. And one possibility is that the magnetic fields within the jet are incredibly turbulent.
Turbulent magnetic fields. What does that mean?
Imagine a river flowing smoothly. Then picture that same river becoming really chaotic with rapids and whirlpools. That's what we think might be happening inside blazar jets. Magnetic fields are all tangled up, and this turbulence could be a way to transfer energy from the particles to the radiation field.
So it's like the particles are bouncing around chaotically in this turbulent magnetic field, losing energy and emitting radiation in the process.
Precisely. And if this energy transfer is very efficient, it could explain why we see lower brightness temperatures than we might expect,
Huh.
based on the sheer power of the jet.
That's fascinating. So it's like the jet is a pressure cooker, and the turbulent magnetic field is a way to release some of that pressure in the form of radiation.
That's a very good analogy. And it highlights the fact that we're still trying to fully understand the intricate processes that govern energy conversion within these extreme environments.
Well, I'm starting to get a sense of just how complex these blazars are, but let's step back for a moment and talk about the big picture. Where does all that energy come from in the first place? How do these systems generate such extreme amounts of power?
That's the million-dollar question, right? And it's one that has captivated scientists for decades. The primary energy source for blazars is thought to be the gravitational potential energy of the supermassive black hole at the center.
Right, so we've got this massive black hole with an immense gravitational pull. But how does that translate into the kind of energy we see in blazars?
Think of it like a cosmic waterfall. As material in the accretion disk spirals inward towards the black hole, it loses gravitational potential energy. This energy has to go somewhere, right? And it gets converted into other forms, including heat, light, and the kinetic energy of the particles in the jet.
So it's like the infalling material is trading its gravitational energy for other forms of energy.
Exactly. And a lot of that energy ends up powering those incredibly powerful jets we've been talking about. But there's another piece to this puzzle that's equally important. It's not just energy production, it's energy collimation.
Energy collimation, with that?
It's about how that energy gets focused into those narrow, powerful jets. It's not just about generating energy, it's about directing it.
So how do you focus all that power into such a tight beam?
That's where magnetic fields come into play again. Think of the magnetic field lines threading through the accretion disk and the black hole as a kind of cosmic nozzle, guiding the outflow of particles into those narrow jets.
So the magnetic field is like a cosmic funnel, shaping and directing the flow of energy.
Exactly. And the strength and configuration of those magnetic fields can have a huge impact on the shape, power, and direction of the jets we observe.
This is starting to paint a more complete picture of how these blazars work, but I have to imagine that modeling these systems is incredibly complex.
You're absolutely right. Modeling blazars is it's a computationally intensive task that requires sophisticated simulations and a deep understanding of physics. We have to take into account things like general relativity, the interaction of magnetic fields and moving plasma, particle acceleration, and radiative transfer processes.
Wow. That's a lot to juggle. And I'm guessing these models are constantly being refined as we gather more observational data.
Absolutely. Every new observation from telescopes like the Event Horizon Telescope and from multi-messenger observatories like IceCube, it provides valuable insights that help us refine our models and test our theories.
So it's a constant back and forth between observation and theory, each informing and pushing the other forward.
Exactly. And that's what makes studying blazars so exciting. We're constantly pushing the boundaries of our knowledge and trying to unravel the mysteries of these cosmic powerhouses.
Well, I'm definitely hooked. What are some of the specific challenges that scientists face when trying to model these complex systems?
One of the biggest challenges is dealing with the enormous range of scales involved. We're talking about processes happening on the scale, the event horizon of a black hole, which is incredibly small, all the way up to the scale of the jets, which can extend for millions of light years.
So you're trying to model everything from the microscopic to the megascopic.
That's the challenge. And it requires developing models that can bridge these vast scales and capture the interplay of different physical processes across those scales.
That sounds incredibly daunting. Are there any specific areas where scientists are making progress in modeling blazars?
One area of active research is in understanding the formation and acceleration of the jets. We've talked about how magnetic fields are thought to play a key role, but the exact mechanisms are still being investigated.
So we're still trying to figure out how those jets get launched and reach such incredible speeds.
Exactly. And another area of focus is in modeling the radiation emitted by blazars. This involves understanding the processes of synchrotron radiation and inverse Compton scattering, which are responsible for producing the light we observe across the electromagnetic spectrum.
Synchrotron radiation and inverse Compton scattering, those sound pretty complicated.
They are. But in simple terms, synchrotron radiation is produced when charged particles, that's electrons, spiral around magnetic field lines. And inverse Compton scattering happens when a low-energy photon collides with a high-energy electron, gaining energy in the process.
So we're talking about like different ways that light can be produced in these extreme environments.
Precisely. And by studying these different radiation mechanisms, we can learn more about the physical conditions within blazar jets and the processes that govern their energy output.
This is mind-blowing stuff. It's amazing to think that we can like glean so much information about these distant objects by studying the light and particles they emit.
It really is a testament to the power of science and human ingenuity, that we can probe the secrets of the universe from our vantage point here on Earth.
So where do we go from here? What are some of the big unanswered questions that scientists are still grappling with when it comes to blazars?
One of the biggest questions is how blazars impact the evolution of their host galaxies and the surrounding environment. We've talked about some of the clues we have, but there's still a lot we don't understand about the complex interplay between these objects.
So while we've learned a lot about blazars, there's still much more to discover.
Absolutely. And that's what makes this feel so exciting. We're constantly pushing the boundaries of our knowledge, and every new discovery opens up new avenues for exploration.
Well, I'm definitely eager to see what the future holds for blazar research. But before we get ahead of ourselves, let's take a closer look at the broader implications of what we've learned so far. In part 3 of our Blazar deep dive, we'll explore how these fascinating objects connect to the grand scheme of galaxy evolution and the evolution of the universe itself.
Stay tuned, because things are about to get even more cosmic.
All right, welcome back for the final part of our Blazar deep dive. We've gone from the structure of these things to their crazy jets to how they might actually shape entire galaxies.
Yeah, it's pretty amazing how much these objects can influence their surroundings, even on like a cosmic scale.
Exactly. And you mentioned earlier that blazars might play a role in the evolution of those massive groups of galaxies, the galaxy clusters.
Right, galaxy clusters. They're these gigantic structures with hundreds, even thousands of galaxies, all bound together by gravity, and they're filled with this hot, diffuse gas called the intracluster medium.
So how do blazars fit into all of this? How do they interact with galaxy clusters?
Well, we've observed these powerful jets from blazars actually interacting with that hot gas in the clusters. It's pretty incredible.
So it's like these blazars they're like injecting energy into their surroundings, almost like they're stirring the pot.
That's a good way to put it. And this energy injection can have a pretty significant impact on the evolution of the entire cluster. For example, it can heat up the gas, preventing it from cooling and collapsing to form new stars.
Oh, wow. So in a way, these blazars they're like cosmic regulators, controlling the rate of star formation in these massive clusters.
That's exactly right. And this regulation of star formation can have a ripple effect throughout the cluster, influencing the properties of the galaxies within it.
It's like a delicate cosmic balancing act, with blazars playing a crucial role in maintaining the equilibrium.
Yeah. And keep in mind, this influence extends far beyond the boundaries of galaxy clusters. Remember that blazars are also these powerful sources of cosmic rays and neutrinos.
Right. Those high energy particles that can travel like incredible distances across the universe.
Exactly. And they carry a tremendous amount of energy. And as they travel, they can interact with other matter, influencing the evolution of the intergalactic medium, that vast space between galaxies.
So it's not just about the immediate surroundings of the blazar. These particles are like spreading out and shaping the cosmic landscape on a grand scale.
Exactly. And there's even speculation that blazars might have played a role in one of the most significant events in the early universe, the reionization era.
The ionization, right. I remember reading about that, but I could use a refresher. What exactly happened during that era?
So in the very early universe, shortly after the Big Bang, the hydrogen gas that filled space was mostly neutral. But as the first stars and galaxies began to form, they emitted radiation that ionized this hydrogen gas, splitting it into protons and electrons.
So it's like the universe went through a phase transition, transforming from a neutral state to an ionized one.
That's a good way to put it.
Yeah.
And this reionization process was a pivotal event in the evolution of the universe. It paved the way for the formation of the structures we see today.
Okay. So where do blazars fit into all of this?
Well, some scientists believe that the incredibly powerful radiation emitted by blazars might have actually contributed to the reionization process. They argue that the extreme energy of these objects could have ionized significant amounts of hydrogen gas in the early universe.
Wow. So blazars might have been instrumental in shaping the universe as we know it.
It's an exciting possibility, and it really highlights the fact that these objects are not just, fascinating curiosities. They're potentially key players in the grand cosmic narrative.
This is incredible. We started by exploring the structure and behavior of blazars, and now we're talking about their role in shaping galaxies, clusters, and even the evolution of the entire universe.
And the journey of discovery is far from over.
Right.
As we continue to gather data from, powerful telescopes like the Event Horizon Telescope and innovative observatories like IceCube, our understanding of blazars will only deepen.
It's like we're peeling back the layers of the cosmic onion, revealing new and more profound insights with every discovery.
Yeah. And who knows what incredible wonders await us as we continue to explore the universe with, ever-increasing precision and ingenuity.
Well, on that note, I think it's time to wrap up our incredible deep dive into the world of blazars.
It's been a thrilling adventure, really.
Yeah.
Through the realm of extreme physics, mind-boggling phenomena, and cosmic mysteries.
We've learned so much about these incredible objects, their structure, their behavior, their energy production, and their profound implications for our understanding of the universe.
And we've hopefully sparked a sense of wonder and curiosity in our listeners, inspiring them to keep exploring this vast and mysterious cosmos.
So to all the budding astronomers out there, keep looking up, keep asking questions, and never stop exploring the universe around you.
Until next time, keep diving deep.
And as always, thanks for listening.
This is your need to know.